Okay, hello. We're going to be working on substitution today, which is another way to find the solution to a system of equations. Now, what that means is we're trying to find an xy point that makes two equations true at the same time. Now, we learned in special cases, sometimes you have no solution or infinitely many solutions. And we'll have to look out for that. But remember, the goal is to find a solution to this system. But what that means is you want to find an xy pair that makes both equations true. Or maybe you fall into one of these other cases. So we'll take a look and see what that looks like. All right, so a solution is a pair of points that makes each equation true, which is what I just said. So another name for a pair of those points is also called an ordered pair. Ordered meaning that it's x first and then y. Okay, so we just did graphing, which Desmos makes graphing really easy and a really good tool. And if you were trying to do questions like this 2 years from now, you probably would just use Desmos. But there's a lot to learn with the algebra and substitution, which is why we're doing it. And it's kind of like a key checkpoint to high school math. You'll use this if you continue on with math too. This will come back up. So it says solve the following system using substitution. Okay, so I'll do the first one and then we'll go over the rules, the steps, and then we'll do the rest of them. So I like to label my equations first, and then I just kind of go through some steps. So step one is we want to isolate a certain variable. So you have to pick an equation and isolate it for either x or y. But my first equation is already solved for x, right? So I can just move on to step two, which is plugging it into another one. So it's going to be substituting 1 into 2. So what that looks like is anywhere there's an x, I'm going to replace it by y minus 2. Right? We're subbing it, x gives us the first equation gives us a definition. It says that x is the same as y minus 2. So everywhere there's an x in the other equation, we can replace it with y minus 2. And the reason why we do that is because now we can solve. If I just do some quick math here, and we get 4. Okay, so the last step is to then, which I think is sometimes the easier step, is to, it says substitute the value into the previous equation to find the remaining variable. So I just pick the one we subbed, so the one we started with, which was 1. You can't just use you can't use this equation that you just started with. You have to go back to the original and plug in 4. So, for example, I want to call this back substitute to remind us that we have to go back to the beginning. And I want to choose number 1 simply because I think it's simpler. So when I do that, I do get 2 as my answer. So this together makes the point 2, 4 our answer. It's the solution. That's where those two lines intersect. Okay, so we've seen a graphical approach, but this is the or one of the algebraic approaches to this. Okay, so those are the steps again if you want to take a photo of that or see that. This is all on Schoology too. So I'm just going to kind of go through and I'll write out the steps for the next one, but for the other ones, I'm just going to kind of go at it. I'm going to do this one next. So this is my first, this is my second. So the first step is to solve one of the equations for x or for y. So this one seems pretty easy to solve for x, so I'm going to do that. All the other ones have 2's in front of them, so I'm going to solve for x here and call that, I'll even box this. Okay, so this is then a key that goes into the other equation. So I want to plug what I just found out x was into the top one. Okay, so this was step 1. And now I'm doing step 2, which again involves a little bit of algebra. It looks like I'm going to be solving for y. And there you have it. Okay, so step 3 is to take 1 and plug that into any equation that you want. So how about this top one? If I know this is 1, I go ahead and plug that in. So you're back substituting this back up to one of these in for y, and I picked the first one just because. So ultimately all we get is just x equals 4. So this would be the solution to that system. Okay? Go ahead and try this one. Go ahead and pause and then see if you can work this one out before you continue, okay? Okay, so without writing out every single step, this y is the same as that y. So if I plug that in there, I now have an equation that only has x in it, which is amazing because now I can solve for x. And then all I have to do is back substitute. So I'm going to use the first equation, plug in 1. So it looks like y is 0. So again, you can pick whichever equation you want. You can pick either. You can always pick the first one if you want. But yeah. Okay, so it's really not too bad. All right, and I'd like you to work out this one and see if you can find out why this is the answer. Okay, and my hint would be maybe to try and solve this for y first. And then make a substitution and then back substitute to find your second point. So see if you can figure out why that's the case. Okay, I want to get to this word problem. So it looks like a snack bar sells 2 sizes of snack packs. The small one is $3 and the large one is $5. So in one day, they sold 60 for a total of $220. So how many snack packs of each kind were sold? So I'm first going to label the small one as x and the big one as y. So x is the number of smalls that are sold, and y is the number of large that are sold. It's really important to get a variable down, right? So if I sell 3 smalls, I want to make $9. If I sell 10 smalls, I'm going to make $30. How am I getting those numbers? Well, that's because it's $3 times however many you sell, right? That's going to equal, if you combine that with the $5 times the number of larges you have, that should equal the $220. So do you see where I got that? It's $3 for each one times the number that you had of that plus the dollar amount you got from the large ones, and that's equal to $220. But it also says that you sold 60 in total. So X and Y are numbers of snack packs. So those together added, the sum of them should be 60 as well. Cool. So what's the first step? The first step is to isolate for either X or Y. So I'll just go ahead and subtract Y, get X by itself. And then I'm going to take this equation and this one. This is my substitute step. Everywhere there's an X in the first one, I'm going to replace it with this. So this is our key, right? It goes into the other equation, the other one, not this one. You don't substitute it back into there. You'll just get nothing out of that. You sub it into the other one, and then you end up with an equation of one variable, y, and it is very fair to solve this. So it looks like I got that y is 20. So what does that mean? That means that there were 20 large snack packs that were sold. Okay? And you might be thinking, hey, well, if it's 20, then I must have sold 40 small ones because that it has to add to 60. And you're exactly right. We have this equation that must be true. We're told that it's true. So if I know what y is, then I can find out what x is, can't we? But, so the back, and this is the back substitute. So back sub. So isolate, substitute, back substitute. It's 3 parts, all right? But that's that's that. Now, if you just kept it here, I don't know if like someone like a 5th grader would know how many snack packs of each kind were sold. Like, it just doesn't really communicate anything, honestly, to someone who's not involved in the math. So I would say you sold 40 smalls and 20 larges. Just write at least a bit of a sentence so I understand what you're talking about. Okay? All right. There's just a little tiny bit more. And these are bringing up of course, our good special cases, right? So we could have one solution, which has been true for all of these, right? It has one XY pair for all of these that are written here. So those all are traditional, predictable, we expect that to happen. But remember, we can also have 0 solutions or infinitely many solutions. Okay? So if I go ahead and use some substitution to solve these, let's see what happens. So I'm going to go ahead and take the top equation, because remember, our first step is to isolate one of the equations. So I'm going to move the 3x over here, and now I get an isolated equation for y. Okay? And then I'm going to go ahead and take the second equation and plug in what I found y is. Okay? And as we go through this, we get to a little bit of an interesting thing happening. Because -6x's plus 6x's They cancel each other out, and we get 0. And if you have 10 equals 10, right, that's the same thing as just 0 equals 0. But what's important is at this point, we see that 0 equals 0 is always true, right? You can't come up with a reason when 0 isn't 0. 0 is always 0. So this is always true, which means that we have infinitely many possible solutions. Because anything you pick for x, for example, it's just going to get canceled out, you know? And it's not even going to matter what you plug in. Anything you want. If we picked x was 1,000,000 and y was, well, not necessarily, but there's a lot of different points. If x was 1,000,000, then we would have to solve the equation and find that y is 3,000,005. But basically, you can pick anything you want for x. I can find you a y that can pair up with it. All right. So this is our this is our infinitely many solutions case. There's not just one intersection. These lines are the same, right? Both of these lines are identical. If you want to go from one to the other, you multiply everything by 2. Okay. You see how you can get from this equation to this equation by multiplying both sides by 2. So another reason why they're basically the same line, because they are. You can use algebra to go from one to the other. Okay. So it's important to know kind of the structure, like going into the problem, what to expect, right? And that sort of thing. Because I also see that, oh, maybe we multiply this times -3 to go from one to the other, but you'll see that that doesn't really work over here with these. So let's just see what happens. So if I want to go ahead and solve this, isolate it, I choose to isolate x because it's already has a coefficient, a number out front is 1. And I like that. Then I don't have to divide or anything. So this is the key. I put the key into the other equation. And from there, it's just about going in, solving. So look, I see these 15 y's that are going to cancel again. Okay. And lo and behold, we get something that just doesn't make sense, ever. It is never the case that 6 is the same as 14. So this would be a, this is a never true. So this is a no solution. So you should be thinking, with no solution, you should be thinking of lines that never touch. Never true. It's never true that both are true, okay? So these lines have the same slope, but they don't hit the y-axis in the same spot, okay? So, and you can graph any one of these, anything on here, and you'll see kind of that behavior showing up on Desmos. All right, cool. Well, always reach out if you have any questions about this.